Good morning, class.
Good morning, sir.
I'd like to talk about a special kind of trigonometry today, something called spherical trigonometry. We know that trigonometry involves triangles. Can someone give me a nice definition of a triangle? Just raise your hand. A nice definition. Actually, even if it's not that nice, it's okay. Yeah, Alvin.
A triangle is a geometric figure with 3 sides and 3 angles.
Okay. Let's look at that definition. A triangle is a geometric figure with 3 sides and 3 angles. Now that's a good definition, but we need to be more precise. For example, is this a triangle? Do you think it's a triangle? This one, this thing that I've drawn on the board. No. Why isn't it a triangle? Alvin, why isn't it a triangle?
Because the third side is not made with a straight segment.
Okay, with a straight line. So the sides have to be with 3 straight sides. Right? So if we don't use an exact definition, there will be some problems later on, and there would be some misunderstandings. For example, is this a triangle? It's composed of 3 sides, right? But is it a triangle? No. Actually, with your definition, it's not a triangle because there are no 3 angles. We can actually replace this phrase here and 3 angles and just make an additional condition that it's a closed figure. That should be enough for us. So a triangle is a closed figure with 3 straight sides. But what is a straight side? What is a straight line? I'd like a definition of a straight line. Can someone else give me a definition of a straight line? How do we define a line? How do I say this is where the line is? How do I locate it? How do I define it? When you draw a line, let's be more specific. When I say a line kasi, I'm implying na there are many ways of defining a line. And one way to define a line is something that has no length, something that's infinitely long. So let's be more specific. Let's take a look at a line that has a finite length, a line segment. How would we define a line segment? We can define, yes, GJ?
It is the distance between 2 points.
Yeah, we could say that the length of the line segment is the distance between 2 points. And we could define a line segment as, well, if these are the 2 points, and we define the line segment as the distance between the 2 points, there are many ways of measuring distances. One way is to do it this way, another way is to do it that way. We're looking for the shortest distance between 2 points. So we can define a straight line as a line having the shortest distance, 1 with the shortest distance between 2 points. We're going to come back to this later, no? Now, if you think about it, a triangle has 3, like it was mentioned earlier, it has 3 angles. We can actually define it as 3 line segments joining 3 points. Now, whenever I have 3 points, I can actually form a straight line or a triangle. For example, if we have 3 points denoted by Gerald, Eunice, and Ezel, they would form a straight line, and that is not a triangle. But if we have 3 points that are not collinear, they have, for example, si Alvin, si Maria, and si Jo Andrea, we would have a triangle. Okay? Now, how do we measure the distances between them? It's easy to get the straight line, and just one person going from to the other. Si Jo Andrea wants to go to Alvin, she won't turn left, she won't turn right, she won't go up, she won't go down. She'll just go directly straight to Alvin. That is what we define as a straight line, the shortest distance. Now, one property of triangles has to do with the angles, the interior angles. For example, we have Alvin here, we have Joe Andrea here, and we have Maria here. We can actually measure these three angles. We can call them angle A, angle J, angle M. What can we say about the measures of these three angles? Something that is true for all triangles. Yes, Joe Andrea?
The sum of all the angles in the triangle is equals to 180 degrees.
Yeah. We can actually say angle A plus angle M plus angle J, or any interior angles, the sum of the three interior angles of a triangle is always equal to 180 degrees. You may even have a mathematical proof for this, you know. So that is always true. Now, for example, I asked Alvin and Joe Andrea and Maria to stand up, and then we measured the angles. How do we measure the angles? Maybe we use a protractor, and then we measure the angles, and then we add them up. It's possible that we won't get exactly 180 degrees. We might get 179 or 181 degrees. Now, that would be my fault. It would be, maybe it's because I'm not very skilled at measuring, or maybe because the protractor is not so accurate, but we know that it should be 180 degrees. If we do not get 180 degrees, it would be our fault, okay? Now, we are pretending that Alvin, Maria, and Joe Andrea are on the same level. Anywhere they go, if they're on the same level, they would always form either a straight line or a triangle. But it's also true even if they're not at the same level. For example, if one of them is in the 3rd floor, another one is in the 12th floor, and another one is in the 5th floor, they would still form a triangle wherever they are. Well, either a straight line or a triangle. But let's keep things simple. Let's say that the three people are always at the same level. For example, sea level, but we're near the sea. So let's say they're always at sea level. Now, for example, let's say Alvin went to the 1st floor. Maria went to the Philippine General Hospital, not so far away. And then Joe Andrea went to, for example, Rizal Park. Okay? Now, my question here is, would they still form a triangle? Well, they could either form a straight line or they could form a triangle, right? But now we have to define more clearly what we mean by a straight line. Because they're a little more farther away, I don't think they would be able to see each other. And if I asked one, can you go, Joe Andrea, can you go on a straight line towards Alvin? She might not be able to do that because there would be things in the way. For example, buildings, diba? Or maybe there would be water or whatever. So I'm going to define the term straight line in a different way. And to do that, I'm going to tell you that I'm using a different definition of a straight line, I'm going to use something called square quotes. Or if I don't have a whiteboard, I would do it this way. I would say straight line. When I do something like that, I'm trying to tell you that I'm using the term in a different way, in a special way. I'm going to define a straight line as the distance from 2 points, the distance between 2 points when along sea level. Let's assume that the three people are always at sea level. Wherever they go, any two of them, to define a straight line, you would walk always along at sea level. Let's say we gave them some superpowers. They can pass through walls, they can float in the air, they can walk across water, just as long as they're always at sea level. They would still form a triangle, right? And if there was a way to measure the angles, a special kind of protractor, maybe we'll use lasers and sensors and something, the sum of the three angles should be 180 degrees. We have a mathematical proof of it, right? Now, let's do something a little different. Let's say we bring Alvin to the North Pole. This is the North Pole, right? And let's say we bring Maria somewhere in Singapore. Ito si Singapore. And we put Jo Andrea somewhere in Africa, in Congo. Okay? It would be somewhere here. Now, I can actually describe these locations using two numbers, if you remember, latitude and longitude. I could say that the North Pole is 90 degrees north of the equator. That's 90 degrees latitude. I could say that Singapore is on the equator, so that's 0 degrees latitude, and it's 105 degrees east of Greenwich, 105 degrees east. Congo is actually at 0 degrees latitude on the equator, and it's 15 degrees east of Greenwich. Now, we have defined a straight line to be the line that is always along sea level. Please use, I'm using a different definition of straight line. And if we do that, you will see, let's try to create our triangle. Okay? Okay. What does this angle look like? How many degrees do you think this angle is? It looks like a 90-degree angle. How about this angle here?
90 degrees.
Yeah, it also looks like a 90-degree angle. How about this one? Yes, it looks like a 90-degree angle also. So what? I have here defined a special kind of triangle using straight lines on these 3 points. And it's a little weird because I got here a 90-degree angle, a 90-degree angle, and another 90-degree angle. Their sum is not 180 degrees, it's 270. Maybe I made a mistake. Maybe it's not 90 degrees, maybe it's 89, maybe it's 91, but it's still not equal to 180 degrees. So this kind of trigonometry is not the same as the one that was usually taught in high school. The things that you learned in high school does not apply to this special kind of trigonometry. What's different about it? The lines are not really straight. If you look at them, they're actually curved, right? So that's not actually a very precise way of describing these lines here. The lines are always on the surface, but they are not actually straight. Now, if we have a trigonometry, if we have definitions and we have terms, and we're talking about the surface of a sphere, not a plane anymore. Now, we're not talking about plane trigonometry. We're talking about spherical trigonometry. And spherical trigonometry is quite different from your plane trigonometry. One example is the sum of the 3 angles in a spherical triangle. Let's call that a spherical triangle. The sum of the angles, the interior angles in a spherical triangle are no longer equal to 180 degrees. Many properties that you learned in plane trigonometry no longer apply to spherical trigonometry. In spherical trigonometry, it's possible to have a shape, a polygon. A polygon is a close-sided figure with straight sides. It's possible to have a polygon with just 2 sides. We cannot do that in plane trigonometry. Can anyone imagine what, Alvin, can you draw for me a 2-sided polygon on a sphere?
From the pole to another pole, we'll draw a line. Then from the South Pole to the North Pole, I will also draw another line.
So here he has drawn a polygon on the sphere composed of 2 straight lines. It's a closed figure composed of straight lines, and it has 2 sides. Now, what would be a nice name for that? Actually, there is already a name for a shape like this. If you think about it, it looks like a crescent. This thing here is actually called a lune. In this case, it's a 2-sided polygon on a sphere. A spherical triangle is a 3-sided polygon. Let's go back to the spherical triangle that we looked at earlier. The one with the vertices at the North Pole at Singapore, somewhere here, and at the Congo, somewhere in Africa. We say that this spherical triangle, the angles are 90, 90, and 90. That is because we restricted the term straight line to be somewhere along sea level. But if you think about it, if you really got the shortest distance between these 2 points, you would have to dig under the ground, no? It would have to pass through the earth. But if you think about it, you would create a flat triangle whose sum of the angles would be 180 degrees. It would actually be a 60, 60, 60 triangle. Now, we can see that from our plane trigonometry, we have counterparts in our spherical trigonometry. For example, in plane trigonometry, we have an ordinary triangle. In spherical trigonometry, we have a spherical triangle. In plane trigonometry, we have a line segment or a line. Let us recall our definition of a line. In plane trigonometry, a line is straight and it's infinitely long. What does that mean? It means that if I walk along a line, I will never stop and I will never go back. I'm just going both ways in infinite directions. But in a sphere, if I walk in a straight line, what will happen? Sooner or later, I'm going to go back to where I started. So that means the line in a sphere, you could say it has an infinite number of points, but it's not infinitely long. It doesn't really start and end somewhere, but it has a finite length. Now, what can I say about that line? For example, this line here, the line on the equator, what can I say about it? If I look at it from somewhere in outer space, it looks like a circle. So lines in plane trigonometry have counterparts in spherical trigonometry. And the counterpart in spherical trigonometry, it's called a great circle. How do we define a great circle? A great circle is a straight line. And that means I just walk not to the left, not to the right, not up, not down. I just walk straight ahead and I will form, in this case, a great circle. Now, what properties of the great circle can we see? We can see that a great circle has a center. The center of the great circle is actually the center of the sphere. The radius of the great circle is also the radius of the sphere. Now, we define a great circle as that circle whose center and radius is the same as that of the sphere. So again, we can look at what we learned from our plane trigonometry and extend it to what we know about spherical trigonometry. For example, we know that any 3 points on a plane can either form a straight line or a triangle. And now we can see that any points on a sphere can either form a spherical triangle or a great circle. For example, points on the equator, any 3 points on the equator form a great circle. So again, the counterpart of the line is the great circle. The counterpart of the triangle is the spherical triangle. Now, is it possible to create a circle on a sphere that is a little different? For example, let us look at this circle here. It's called the Arctic circle. Here we have a circle. This circle here at a fixed latitude is called the Arctic circle. Using what we know about the great circle. Remember, a great circle is a circle whose center and radius is the same as that of the sphere. Look at this circle here. Do you think it's a great circle? No, it's not a great circle because its center is not at the center of the sphere. The center is somewhere here, and its radius is not the same as the radius of the sphere. So this thing here is called a small circle. A small circle is a circle on a sphere that is not a great circle. You can see that the reason why we call it a great circle is because that's the largest circle you can create on a sphere. Any other circle is called a small circle. Let me now put forward two more questions, a little more difficult, something very conceptual. Let's say I'm standing on the surface of a perfect sphere, and then I'm at an arbitrary point and I'm walking in an arbitrary direction. Parang I choose one at random, I choose a point at random, and I choose a direction at random, and I walk in a straight line. Again, we have defined a straight line this way, We're always at sea level. My question here is, if I choose a point at random and I choose a direction at random, will I always be walking in a great circle? We know that circles on the sphere, some of them are great circles and some of them are small circles. My question here is, if I am on the surface of a sphere and I walk in a straight line, any point, any direction, I'm always walking in a straight line, do I have to be walking on a great circle? Or is it possible that I'm walking in some other way? Yes? Do you have a question?
Yes.
Yeah.
Sir, if I can choose any point on the perfect sphere, and I can choose any arbitrary point or direction, then I'd be passing through a point in the great circle, but not necessarily, my path is not necessarily that of a great circle. It could be that of a small circle. If I start at the equator and walk in any direction, then I would be walking in a great circle. But if I start at a point not on the equator, then I'd be walking in a small circle.
Okay. I think I need to clarify something. This is not the only great circle on the sphere. You can actually have lots of great circles. This is one. This is another one. Okay? So there are actually an infinite number of great circles. Now, you were saying that if I was on a great circle, and if I move in a straight line, I would be walking in a great circle. But as you can see, there are actually an infinite number of great circles. And any point that you select will always be on a great circle. So one way of looking at it is this. When you're walking in a straight line, you imagine this, when you're walking on a sphere and you're walking in a straight line, what is to your left? It's half of the globe. What is to your right? It's also half of the globe. You're not moving to the left, you're not moving to the right, you're moving straight ahead. So exactly half of the globe is on your left, exactly half is on your right. And that means you're on a great circle. Okay? Now, we have another, I have one last question before we end our lesson. And it's a very, very nice thing to think about. Earlier, I defined a triangle on the sphere whose sum was 270 degrees. If you think about it, remember, in a plane, the sum of the angles in a triangle is always 180 degrees. Now let's put this on a sphere. I'm going to look at the, I'm trying to bend the surface so that it's part of a sphere. What do I notice? Look at the corners here. It looks like they're widening, right? So this is your plane triangle, and when I try to make it a sphere, the vertex here, the angle here is actually getting bigger. So when I make it into a spherical triangle, the angles get bigger. So what? In a spherical triangle, the sum of the three angles will always be greater than 180 degrees. It can never be 180, because if it was 180, it would be a flat triangle. So in a spherical triangle, the sum of the angles are always greater than 180. Now, this is something very nice. Here I have defined this triangle here. The three interior angles are each 90 degrees. Can you think of a spherical triangle whose interior angles are 270 degrees each? So here earlier we had a triangle where the interior angles are 90, 90, and 90. Can we have a spherical triangle whose interior angles are each 270?
No.
You're thinking, sir, if you were talking about exterior angles, then we could have a 270-degree angle. But you're talking about interior angles. Okay? Now, let us go back to the definition of a spherical triangle. A three-sided polygon on a sphere. And what is a polygon? A closed figure bounded by straight sides. In this case, bounded by great circles. I want to show you something, okay? I'm going to draw a spherical triangle. This is the spherical triangle that I drew. It looks exactly the same, as the one that I had earlier. This is one great circle, another great circle, another great circle. So that's a spherical triangle. But I'm going to define the inside of the triangle in a different way. I'm going to say this is the inside of the triangle. Can I do that? Can I say, earlier kasi I said that this was the inside of this triangle. Can I say that this is the inside of the triangle? There's nothing in the definition that prohibits me from making that assumption. So I can actually make a triangle that looks like this. Can you see? Look at that shaded region. I am claiming that that shaded region is a spherical triangle. That is, if you take the triangle that we got earlier, cut it out, the remaining surface is also a spherical triangle. Can I make that claim? Yes, because this is the definition that I used. I said that it is closed, diba? It's bounded by three great circles. I can actually define this shaded region here to be a spherical triangle. This is the interior. And if that's the case, these also would be interior angles. So in spherical trigonometry, it's very, very different. Because when in plane trigonometry, you define the inside of a triangle as always what's bounded by the three sides. In spherical trigonometry, you can actually define the triangle to be the one outside. So that's a big difference. Before we continue, do you have any other questions about the things that we discussed? Yes, Alvin? Can you, do you need the blackboard? Do you need the whiteboard to ask your question, or can you ask it from there?
Oh, I will do
Okay.
the whiteboard, sir.
Okay. So what is your question about?
Okay, sir, this is this is regarding the earlier statement that you said that if I can choose an arbitrary point in a perfect sphere, and I can choose any arbitrary direction, then I would be walking in a great circle. However, what if I choose an arbitrary point, for example, here, and I call this point A, and I choose a direction that is not parallel to the polar axis. By polar axis, I mean if you connect the two poles in a straight line, even passing through the crust, then you would form an axis here. If I choose a direction that is not parallel nor perpendicular to this axis, then, for example, if I choose northeast of that axis, or if I make an angle, if I choose northeast, then assuredly I would not be walking in a great circle here, but rather a small circle.
Okay. When we talk of a sphere, it doesn't have to be a sphere that is moving. So it doesn't have to be a sphere that has an axis of rotation, or it has north or south poles or whatever. It could be any sphere. In this small circle that you've drawn, the one, let's say you're walking in this direction, the part of the sphere to the left is bigger than the part of the sphere to the right. That's why you created a small circle. If you think about it, how did this part here become smaller? It's because you walked a little to the right. But if you walk straight ahead, not to the left, not to the right, you will see that the left half of the globe, the left part of the globe would be the same as the right part. That is, if you were really walking in a straight line, it would be something like that. So in any direction, even if there is no axis of rotation, even if there are no there are no north, south, east, or west directions, as long as you walk in a straight line, half of the globe will always be to your left and half would be to your right. If you move a little to the right or a little to the left, then you would create a small circle. So I hope that makes things clearer. No? Let's go over the concepts. I'm going to show you a few examples, and you're going to tell me if what I've drawn is a spherical triangle or not. For example, let's say this is the globe, and I draw a triangle like this. So this is on a constant longitude. This one is a meridian, and this is a line here. Would you say that this is a spherical triangle?
Yes, by definition.
If this third line here is somewhere here, would you say that this is a spherical triangle? No. Why would you say that it's not a spherical triangle?
It's not bounded by a great circle.
Yes. Yes, because this circle here would be it's not, the center is not at the center of the sphere. It's not a great circle. And so this thing here would not be a spherical triangle. It would be a three-sided closed figure, but it would not have